Hi, I'm Margaret. I'm from the Milwaukee School of Engineering Center for BioMolecular Modeling.
And I'm Cassidy Terrell from the University of Minnesota Rochester.
And we're going to share with you some materials that we've created under two grants. The CREST grant to Milwaukee School of Engineering. CREST stands for Connecting Researchers, Educators, and Students.
And the Model C grant that is for University of Minnesota Rochester and Kennesaw State University, which stands for, or our acronym is Model C, and that stands for Modeling for the Enhancement of Learning Chemistry. And this model set that we're talking about today is part of a series of models that we've designed that target enzyme substrate misconceptions that have been documented in the literature that undergraduate biochemistry students hold in relation to how enzymes and substrates interact, and a little bit about how I teach and where these models come into play. So I teach undergraduate biochemistry course that meets 3 days a week, and it's 50 minutes each time, 50. The students watch a video outside of class, answer a few questions, and then they come into class with a little bit of content knowledge, hopefully a little bit of practice, and then we work on that content again in class. And so my enzymes unit starts, the first day is just how enzymes and substrates bind, thermodynamics, electronics. The second day is an application of how enzymes and substrates bind, which is part of this activity. The next day is Michaelis-Menten kinetics, so Kcat, Km, Kcat over Km. And then it's bringing all of that together with the serine proteases, enzyme inhibition, and then how do you use all this information to design inhibitors using the HIV protease as an example. So this model set that I'm going to talk about was inspired by a practice problem in the Leninger textbook. And again, I use this model set on 2 days. The second day on enzyme substrate binding, enzyme transition state binding, and then again on Michaelis-Menten kinetics. So in the practice problem, which is based on literature on the lactate dehydrogenase enzyme, the paper goes through how the enzymes and substrate binds, how the enzyme preferentially binds a transition state, and that's why I thought this one was a really awesome example, because a lot of my students can regurgitate to me that enzymes preferentially bind transition states, but I'm not sure that any of them really understand what that means. And maybe they will only get to see one example with the serine proteases with oxyanion whole, and this lactate dehydrogenase example is a little bit subtle, but really powerful once they get to it. So this is sort of one of the diagrams that the Leninger textbook uses, and was the inspiration for the first model iteration design. So this is the active site, and they've kind of got the shape of it here. And so what we did was we wanted this sort of flexible model here because I wanted to highlight that proteins are flexible molecules. A lot of the models I use are really rigid and they don't move. And then the active site residues are placed in the same sort of shape here. And what happened the first semester of class is the students had a hard time going back and forth between this model and the paper model and this model and the paper model, and was especially cumbersome once you introduce the substrates with it.
May I try?
Yes. So here the first question asked them to place the substrate here, which is pyruvate, and then this substrate, which is just a section of NADH, it's the functional section, to place the substrates in the best orientation and proximity in the active site. And what you'll notice is, one, you need 2 people at least to do this.
And there's a lot of space in here.
There's too much space. So it's, you know, where you could go at this from any angle, and there was too much space for them to kind of figure out, like, what am I looking at here? Honestly, the cognitive load was just observationally way too high. And another thing that I noticed is that given the chemical equation for lactate dehydrogenase, most of the students wouldn't even put NADH in the active site. They would only use the pyruvate molecule. Anyways, it was a really fun day of class. And I ended up modifying it to make it a little bit simpler for students. So I don't use the full 3D model anymore. Instead, I take a blown up picture of the active site and have the students place the amino acid side chains around so it's more flat. And now we have a conversation about how do you best place pyruvate and NADH in the active site to show the best orientation and proximity. And so the first part of it is just having them understand how the enzyme substrate complex is formed.
So I see a lot of red atoms here that represent oxygen, which is negatively charged. And I see lots of blue nitrogens here. So I guess it goes something like that.
Okay.
It might be, maybe it would be happy that way. I kind of like that.
Okay, I like that too. And so students would probably get somewhere close to this. And then on the board is my opportunity to draw out the mechanism for them. And that way we're connecting that this is an enzyme. It facilitates a movement of electrons. And obviously there's no board here, so I'm not going to draw that out. But what they will notice is that most of them will have gotten this interaction here, right, with these two Mickey Mouse pairs.
Okay, so I'm going to hold this up so people can see
Right.
the two Mickey Mouse pairs.
And many of them may not have realized that you need the NADH because there is a hydride transfer, a hydrogen and H minus, that will attack the carbonyl carbon. And then the other hydrogen,
So this must fit. If this is going to be here, it fits in here somehow.
and it needs to be the hydrogen that will be the hydride that will attack the carbonyl carbon needs to be near the carbonyl carbon. Oh, but you can't move that. That has to be stuck here.
Could I move it?
You can rotate
way.
it. Good.
That makes it a little closer. This kind of has to reach in then, and there doesn't look like there's enough room. So what if I reach it in this way?
So you can do that, but that's not the hydrogen that will be moving.
It's not? Oh, where is it? There it is.
There
Okay.
it is, yep.
They're magnetic, and you have to find the one that's magnetic.
Yeah.
So this has got to come in like this.
Awesome. So that hydrogen will move here.
To there.
Good.
So we moved it from here to here.
Good.
Okay.
And so in the mechanism, the electrons from the carbonyl carbon to the oxygen, the double bonds, will move up to this to become an O minus. And I'm actually going to pause kind of right there before I have you do the rest of the mechanism. This atom, when it becomes an O minus, and this will actually be a carbon with a positive charge, is the transition state molecule. And this is a molecule that they'll see on the paper, not one that can be easily represented here. But then the question is, so they will have an enzyme transition state complex, which is the next phase of the mechanism. And the question asks them, why is this enzyme, or is it, preferentially binding the transition state over the substrate?
That's a great question, and I don't know that I know the answer to it.
So, and again, we also have them draw this on paper. So in the substrate, this is a neutral oxygen, so just a regular O. And this is a positively charged histidine. So the interaction between the histidine and this oxygen is an ion dipole. So
Right
this
here.
is the ion, this is the dipole, and that's a favorable interaction. Once the mechanism is initiated, this becomes an O minus. It's a salt bridge now.
Salt bridge, that's what I
there
was
you go.
thinking.
Yep. So the interaction goes from being an ion dipole, which is stronger than the hydrogen bond, to an salt bridge interaction where both of these are charged. So that is the very subtle example of how this enzyme preferentially binds a transition state. Nothing moved necessarily in terms of shape, but the electronic interaction became stronger,
Okay.
which again is subtle, and using the drawn out like skeletal structures and the mechanism on the board really helps that. But then the students can finish the mechanism to create lactic acid.
And then this
then
goes out.
That goes out. This comes out.
And then the water comes in.
Water will come in and regenerate the enzyme. And so you can talk about how enzymes are catalysts that become regenerated. So there's a lot of concepts here. Definitely you can use this in a lot of different ways. Again, with 50 minutes, I kind of help them along at certain points so that we get through the whole story. And then again, I usually bring this model set to office hours and things like that because students have this look on their face where it's like, what just happened? I need to think about this a little bit more. Maybe I need to do that again. I want to see it again, or 2 or 3 times, and again try to connect what they're seeing with the movement of these plastic magnetic pieces with their conceptual knowledge about how electrons move, how enzymes work, how do we connect this with the graphs that we make in biochemistry, with the representations that we're doing. So there's a lot of layers here. But that's the first day that I use these.
So you have a second day activity for this that involves mutations.
Yes, so the second day is when I introduce the Michaelis-Menten kinetics, so we do KCAT, KM, and I bring this model set back again. It's set up exactly the same way, only now there's a couple extra pieces for them to interact with, and essentially what it does is the authors of the researchers did point mutations. For example, they mutated this arginine 171 to a lysine, so they could switch that out. And again, this will probably already be in here. And this particular, just for an example, this particular question says that the authors noted a really marked decrease in the amount binding, the percent binding. So the KM went up. And so the question is, why?
Okay, and I see here we have one nitrogen to interact with the oxygens, whereas in the wild type enzyme we have 2 nitrogens. So that would increase binding. This improves binding. The mutation decreases binding.
Exactly. And this particular interaction between these two functional groups where you have a carboxylic acid and the guanidinium is it's called forked coplanar, because both of these are planar, which means they're flat functional groups, and it's forked like a fork. And this has a positive charge and this has a negative charge, so there's a shape and an electronic interaction here that's incredibly favorable, and this particular interaction pops up many more times as we go through the course.
Okay.
So while
so
you've
they get
changed
spaced
out
repetition and seeing this.
exactly, so while you've changed one positively charged amino acid for another positively charged amino acid, there is a shape interaction that is really important here. And then you can ask a question, well, they saw binding decrease, but not catalysis. So is this arginine 171, is it involved in binding?
Yes.
Or catalysis?
No.
Both?
Or neither.
Or neither.
And I would say it's binding, but not catalysis.
Exactly, because the KCAT did not change at all. And then there's a couple other questions where, different ones of these are mutated, and we have the different side chains to represent that. And then, again, you kind of go through almost the whole active site, and you can then distinguish which are the catalytic residues, which are the binding residues. Are some both? Are some neither? And then that's how this model helps facilitate the Michaelis-Menten kinetics.
That's awesome because it connects a lot of different points using an active site. And just to mention, these clips represent the rest of the molecule, the R groups.
Yes.
This does not look at all like
H, yeah.
NADH because there's a whole lot more there. But
Yeah.
this is the working part of the molecule.
Mm-hmm.
And for me, that makes it much easier because if I had the whole molecule here, I wouldn't have known which end to fit in.
Right. It's huge. I mean, NADH, that would probably be really interesting for students. It's a really, really big molecule, especially in comparison to pyruvate or even these amino acid side chains. But it's only this small section of the molecule that fits in the active site, so just cut the rest of it off. There's one last little piece that I thought was really interesting about what the authors did, is they did a point mutation up here for this glutamine 102 to an arginine, and that essentially changes the enzyme from lactate dehydrogenase to malate dehydrogenase. And malate dehydrogenase has a bigger substrate. So it's 1 carbon bigger, it's got another carboxylic acid functional group, and then you switched out a smaller amino acid for a bigger amino acid. And the question to the students is, how is it or why is it that when we put a bigger amino acid with a bigger substrate, it still binds really, really well? How does that happen? Like, what happened here?
And that really doesn't show very well in that model, but if you were in this model, you could see that the protein is flexible. So
Exactly.
it makes room for that substrate. And now I see two sets of, what did you call them, planar?
Forked coplanar.
Forked coplanar
Right.
molecules, which
Right.
makes it a super good binding site.
Right, exactly. So the Km for this is really low because now there's two forked coplanars here, so it's essentially tethered down the molecule in this orientation and proximity, which keeps it in line for catalysis.
That's really cool.
It is really cool. Yeah,
I think that's it.
I think that's it. Yeah.